point is you can do it because you're programmers. Okay. Now, before I make it more complicated, so back trace the prev pointers, something like that. There's some sort of pseudocode for breadth first search. How do you feel about this? Any questions? Anything you don't understand about its behavior, how it works, why it works, what it does, when it will do stuff? Or is that just painfully clear because this was brain dead obvious from the beginning?
Yes.
I'm okay with that. That's kind of where it should be. Now let's make it a little more interesting. There's now this terrain map, and this is a ridiculous terrain map that I made in the GIMP. We're trying to get from here to there, and the cost of every single step that we take is non-uniform, even though we're using uniform cost search. Isn't that ironic? Because going this way costs more than going that way, there's a price to be paid. And we're not actually looking for the shortest distance from here to there. We're looking for the cheapest distance from here to there. What's the difference between cheap and short? Cheap and price and length? Is there necessarily a difference? Yes.
In this case?
It's something you can measure. Length is something you can measure, right? I mean, you could say that you have a ruler that gets more dense when you're crossing white and stretches when you're crossing black. And then cost is length. Cost isn't really necessarily a different concept from length. It's just something you can measure. So in this case, we're just measuring something. And according to that measurement, we're going to find the shortest or least cost path from the beginning to end. Do you see that we can actually use breadth first search to solve this problem, even though we're doing minimum cost? Kind of. Well, we can, except not every step has the same value. If you're right here in this black edge between black and white, and stepping into white is really expensive and stepping this way is really cheap, you kind of want these cheap ones to go ahead in the queue because they haven't gone as far yet. But these ones that have gone here are presumably really long. It's as if you've been processing for a while. They should be much later in the queue. So how are we going to solve that issue? Answer, yeah.
Sort your queue by the cost?
Yeah, basically we need a priority queue instead of a plain old queue. When you have costs per step and you still want to do breadth first, it's called uniform cost search because you're searching on a frontier that's not necessarily equal distance, it's a frontier of equal cost. And as long as we search on the frontier of equal cost, as soon as the frontier reaches the goal, the back trace of whichever node reached the goal is guaranteed to be the optimal cost solution under certain circumstances that we haven't yet defined. Okay. How many people have never worked with a priority queue before? Okay. What does one have to do to use a priority queue?
Clear little interface?
Passive inheritor? Import.
Yeah, so import priority queue. Java does it for you. I'm not even going to make you code up your own priority queue. So it shouldn't be too big of a deal. The thing though is it has to sort your objects inside the queue. And that means it needs some way to compare them, some interface stuff. And I'm going to just say that's your problem because this isn't a programming class. Okay? In all fairness, some of you will encounter that and realize that this is a big pain because I don't know that our programming classes really teach all of those things, or at least not well.
They don't.
Yeah, so I'm not going to just throw you to the wolves. Please post on the forum, hey, how do I do this? And I'll give you examples, or ask in some way. Preferably, don't ask just me personally so I can tell you personally because then it doesn't benefit everyone and it uses up more of my time. So if you please post on the forum instead, I prefer that. Plus, maybe one of you will answer it and then I can go play video games or something.
make your own, I thought.
Yeah, but I'm just gonna try to stick to the AI theory and assume you can code. Okay, and I'll do that until enough people come to me with problems, and then I'll come out in class and help you with coding. Yeah.
You wanted us to draw the green lines every, like, what, 5,000 or whatever? When we find the goal, do we stop drawing the green lines, or do we keep going?
Yeah, you stop. So this is a very poor example.
Because it's like crop
Looks off like the
cycling,
monkeys.
and it's like monkey sign.
Oh, let me show you. Let's see if we're ready for this. I think we are. This one. Come on, a little faster. Nope, it's not that one. Sorry, give me just 1 second. I'll show you. Oh, I had it ready. Now I lost it. There we go. Okay, there's a good looking answer for you. Now you can, I don't know if you can see that too well, but down here you notice there's this frontier and that's where it stopped. Essentially it never searched down into this region because as soon as we found the goal we said, okay, good enough, there's an answer at the end. Now, this red line is the optimal path, and you see it actually loops around here, and then it comes down here, cuts across the white. Why didn't it go around the black?
Because it's non-zero.
Yeah, that's not optimal, it turns out. How do I know that? Because this is what I got when I coded it up too, and I make no mistakes. It's not true at all. But it calculates the optimal path way better than I ever could. Because Uniform Cost Search says this is optimal, I assume it is, and I'm pretty sure it's right. So you should end up cutting across the white line. The way you can kind of tell is if you look at these frontiers, you can see they're trying to reach around. The frontier is kind of pushing this black area ahead of other possible paths, right? It's not pushing very far into here. And yet, if you follow the contours, you can see that it's right about this one is lined up with that one that finally breaks free into that black line. So it almost got there, but not quite. So either I could blacken this region a little bit more or lower the white a little bit more. And if it got to just this point where that point right there reached there, see that distance between those two contours? That's the distance between how much better this path is than that path. This is kind of the point of the mountain, where if you stand a pencil on its end, it just stands there and doesn't fall this way or that way because it doesn't know which way to fall. Okay. So if your answer looks like this, you've got it right. If it looks like something else, nope. Okay. Do these contour lines terrify you? Do you know how I got them, or what they do, or does it feel like that's going to be a lot of coding?
No, it was like 3 lines.
Yeah, think about it this way. At the very start, in your queue is nothing. After a few iterations, you've got it's starting to reach out, and you've got all these paths that are kind of spreading out in different directions. And because they're not backtracking, they're only going outward. Well, at any given moment, the ones on the inside are kind of dying off because they're getting popped out of the queue and they have no more neighbors that haven't been visited. So there's really this frontier of expanding units. Whatever's in the queue is the frontier. And that frontier expands and expands until it gets all the way down to here. So these green lines are really just samples of my frontier. I plotted a green dot at every node in my frontier at periodic intervals. And that makes this image. It's really quite simple. The fact that it's all wonky and wavy and has lots of lines is just a visualization of what's going on in my breadth first search over time. So this is time close to 0, time 500, time 1,000, time 1,500, and so forth. We could label them if we wanted to, but this just shows how the frontier expanded, and the frontier apparently reached that point right on that line, showing how we found the goal. Okay, so how did I print this red line?
You trace through the path.
Yeah, I have previous pointers in all of my node objects, we'll call them, where there's a bunch of nodes that go into my queue. And once I get to the end, I just go prev, and I find the XY location of all these nodes, and I put a red dot there all the way back to the start, and that gives me the path. Okay. How do you know the cost of getting from here to the end? How would you compute that?
Nodes on that list have to keep up with the cost of their current.
Yeah, in fact, you're going to have to have every node. Is there a better name for that? Position,
Pixel?
spot, pixel. Okay. You're going to have to know the cost in all of them so that your priority queue can sort them, right? Because that's what the priority queue does. Is it's going to all the cheapest ones are going to go out first. So whatever path is the cheapest on the frontier is always going to be the one we try to push a little farther. And that's why the frontier expands in this way. It's kind of like, suppose this is our frontier. We're going to try to push this one a little farther. Well, now that's the most expensive one because we just pushed it farther. And so they're all going to get pushed a little farther until the frontier is a little bigger. And then whichever one on our frontier is the cheapest, that's the one that gets advanced next. So the whole frontier gets pushed and pushed and pushed out until uniform cost search grows over the whole terrain until the first one that finds the goal guarantees to be the cheapest guy. Okay. I can't think of another thing to say about this algorithm. So that's all of assignment 1. Yeah.
A difference of ideal paths.
Oh yeah, I meant to say that. Thank you for reminding me. Okay. So Aaron, by the way, are you Aaron?
Yes.
Thank you for, by the way, Aaron provided this awesome analysis, and I want to show it off to you now. So these are some results that Aaron got, and these are some results that another student got. And if you look at those, look at that difference. What is going on? Now, if one student turns in this and one student turns in that, the first question that crosses your mind is the grader going to notice? I seriously doubt it. I think if yours looks like this and somebody else looks like that, just turn it in, you're golden. But as far as the learning occurs, you can see they're not the same, right?
The green ones are different.
In fact, we have a diff image. This is the actual difference between these two images, which is kind of cool.
The path's the same, right?
No, it's
The
not.
path,
No.
let's look at the path. Can you see it move?
It looks like it's not moving.
The path it
Oh,
actually
no,
isn't.
No, it's not like at the
Look
top.
right there in the black region you can't see because of the contrast.
And to the right of it.
And watch when you see the red line wiggling slightly?
The blue on the diff image.
It's a
is
nearly
the-
similar path. And at this point, we're gonna say, close enough to optimal, who cares, right?
But why?
No, because this is theory now. We want to know exactly what's going on, why. Turns out if the costs of these paths are identical, there are multiple paths that have identical cost. If your answer is a non-optimal path, I'm going to say that's a wrong answer. I don't know for sure if the grader will catch it, but I will tell you that in theory you're wrong. So I don't turn in a non-optimal path to bug your code. But if you have one of many optimal paths, it's going to be good enough.
Could you tell us the optimal?
I
Number.
can.
Yeah, yeah, it's in the assignment.
I was gonna say, I didn't look all the way along. That's my fault.
Let's see. 65,844. There you go. There's the optimal cost. No matter what path you get, if it's optimal, it's going to follow this general scheme. There are no optimal paths that go completely different. Is it possible for an optimal path to go totally different?
If I redraw the picture.
In some other picture, yes, that could very well happen. in this one, there's nothing else that's very unlikely though. Usually you'll get optimal paths that differ by a couple of pixels and nobody really cares. I don't know exactly why. I'm guessing somewhere around here there's a couple pixels that are the same, a couple neighbors that have the same cost. Why, though, two people coded up the same algorithm, why do we get different answers? Where is the non-determinism in this?
In their implementation.
In their implementation, yes. I guess what I'm trying to get at is where in their implementation is the non-determinism?
Sorting of the queue.
Yeah, so you've got priority queues, and your priority queues have to take all of these nodes on the frontier and sort them by which one comes first, right? This one has a cost of 23, this one has a cost of 23, which one comes first?
Doesn't matter.
Doesn't matter, so it ends up maybe flipping them, maybe not flipping them. And yet, does it use a random number generator? Probably not, so still, why is there non-determinism? Shouldn't it have arbitrarily produced the exact same results if they use the same Java priority queue? Well, it depends which one they put in first. Suppose you have a queue, and you put one into the queue, and it gets sorted down, bubble, 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 and it's doing this comparison. Even if it's totally deterministic, if you put this one in first, it could end up in a different slot than if you put the other one in first. Do you agree? So what it has to do with is the order in which you put it into your priority queue. One of them coded it up. Here's my point. Try north, try south, try east, try west. One of them coded it up. Try north, try west, try south, try east. Or something like that. I don't know exactly what it was. But if you push them into your queue into different orders, that's enough that when you get two things that are equal, it'll munge up the queue. This is where chaos happens. Unless you do exactly the same things, there'll be a little bit of chaos. So everyone's answers are going to differ by about that much, and I'm totally cool with that. Now, if I had assigned continuous costs to all of these instead of discretized costs, it probably would not happen. You would all get identical results. In this case, I used the green channel of the pixel as the cost for moving. Is it the green channel of the one you're moving onto or the green channel of the one you're moving off of?
Onto.
Is it onto? Thank you. I haven't done this assignment in long enough, I don't remember. So it's the color of the pixel you're moving onto. I think that makes sense, but there's only 255 values, so it's quite likely there's some duplicate here. If they were continuous, you'd all get the identical results, even if you visited in different orders, because there would be no two neighbors that have exactly the same cost. And the number one question that everybody asks me about on this assignment is, do I have to get your 0.45 seconds? No, I don't care. The reason I put that there is some people keep telling me, mine's been running for 45 minutes, should I keep waiting? No. If you're 10 times longer than that, press Control-C, debug your code. I'll tell you what your problem is. If you're taking a long time, think about it this way. Well, first of all, I've already told you if you're backtracking, it's going to take forever, right? So you know that's one possible cause. Suppose that you visited every pixel in this image, one at a time, and at each one you did some amount of computation, where some amount is, I don't know, maybe 100 pages of code worth of computation. How long would it take for you to raster across this image and do 100 pages of computation for every single pixel?
250,000 times.
Okay. It would, you know, maybe it'd be slow, but it would still sweep across this image in a pretty reasonable amount of time because computers are darn fast. So I can guarantee you, if it's taking a long time, you're visiting some of these pixels more than one time. Doesn't that just follow rationally? I mean, yeah, it's possible you did so much computation on one pixel that it slowed you down, but does anywhere in your code do a lot of computation per pixel? I know it doesn't. Therefore, if it takes a long time, your problem is your backtracking is broken, or your I've been there detection is broken. Okay.
Can I make another suggestion?
Yes.
There is one thing that you do But if you're doing per pixel, it can take a lot of. Take a lot of time.
Okay.
If you're reading in the image on a per pixel basis, that takes a long time.
Ah. Does anybody do that? Why would you read the image on a per pixel basis?
I was the one that posted on the forum that it took 35 minutes. I moved that out of my while loop and it ran in 3 seconds.
Ah. Okay. There you have it. Don't do that. Unless you want to, in which case that's cool.
Try to wear out your hard drive as fast as possible.
Yeah. Don't resave your image after drawing every single pixel. Don't. There are a few other good ways you could really do it. Don't just stick an endless loop in the middle of your program. Don't forget. Yeah. Okay. I think we're done with assignment 2. Done talking about assignment 2. I'm glad about that because I want to talk about assignment 3, and here's the main reason. Those of you who went ahead and just did assignment 2 are probably going to be a little mad at me. Assignment 3 is the same assignment on a totally different problem. Here's my rationale for that. So here's the problem. It's solve this puzzle. When you code something up for a specific problem, do you see how that's recording human intelligence? That's not really artificial intelligence, is it? I mean, that's kind of debatable, kind of vague. It's not even clear what artificial intelligence is. I started this whole class by saying it doesn't exist. But I don't think there's a difference between AI and human intelligence. But if you can write a general solution such that you could take this one problem and try it on a different problem, and it works again, that feels more like AI to me than if you just coded up a solution to one problem. Do you agree with that? I mean, AI should generalize. In fact, there's a really great YouTube. I have been searching for this YouTube since I saw it, and I cannot find it. So if anybody finds this on YouTube, please post it to the forum or something. That would be awesome. There's, it is Deep Blue versus Kasparov the rematch. Do you know what I'm even talking about?
Chess?
Kasparov is the world chess grandmaster for some period of time. And Deep Blue is a big machine built by IBM. It's a big rack of servers. And it was designed to play chess. And it was the first computer that really beat a chess grandmaster at chess. I don't know if I know the details very well. Turns out there's some controversy about it. The IBM programmers were working on their program while the game was in play. Kasparov found out about this after he was beaten and claimed that they cheated because he was actually competing against 30 men, not against one machine. And so it was supposed to be this big John Henry moment, you know, man versus machine, can man defeat the machine? And the machines won. And then they debated whether it was legitimate or not. It was years later before they finally did a rematch. The answer's in, humans suck, machines rule. Machines are just way better than humans at chess. That's just the way it is. But the people that are the hardcore human defenders will keep pointing out that the modern chess grandmasters refuse to play against machines, wisely so. And no machine has proven beyond doubt, without doubt, without playing by all the rules and doing it fair, that computers can beat humans at chess. So it is technically still up in the air. We don't know for sure machines can beat the best humans, but they cream really darn good humans every time. Yeah.
Are you talking about the screen capture of the game from 1997?
Oh yeah, I was telling a story. So here's the YouTube video. It's the rematch. Obviously, if there's a failed game, you have to do a rematch. This one takes place at a swimming pool. So they've got Deep Blue propped up on a diving platform, this big rack of machines, and Kasparov in a Speedo, and he looks terrible. And it's not the real Kasparov, by the way, it's some actor trying to be Kasparov. Somebody fires a gun, Kasparov dives in the water, Deep Blue. I just spat. All kinds of sparks, it fizzles and dies. The point is, obviously, machines stink at generalization. Whereas humans, while maybe they can't beat the machines at chess, you put them in a new problem, like swimming, the machine suddenly can't do anything. you ever seen a robot try to walk upstairs? I mean, they're pathetic. They fall on their face, they can't even open the door. As far as advanced as AI is, we just don't have machines that can solve general problems. Okay, the whole reason for that big old tangent is I'm trying to force you to write general code. Because if it's more general, then it's more like AI. So if I make you solve two different problems with your same approach, in this case uniform cost search, then the only way you'll pull that off is if you can write pretty general code. Or if you do it twice, your choice. I think the intelligent student will usually choose to write one general solution well rather than write two solutions badly. I guess you can choose which way you want to do that. But if you think about that in advance, then you'll realize that, hey, you could design your uniform cost search so that you could do assignment 3 now and save yourself a bit of work. So sorry for those of you who already did assignment 2. But now you probably want to rewrite your code just a little bit to handle assignment 3, and then you'll do the next job. Okay. So let's talk about assignment 3. How much time do I have? 20 minutes.
20 minutes.
Looks like. Okay. So assignment 3 is solve this puzzle, whereas assignment 2 was find the lowest cost path. What do these even have to do with each other? How can you use the same algorithm to solve both of these problems? Can you even see that at all?
We want to solve some puzzle using the minimum number of moves. So
Yeah.
there's kind of an analogy there.
So, the reason I start you out on a path search is humans are really good at temporal-spatial reasoning. We understand getting from here to there. It's the kind of problem we do, right? Humans are not very good at this type of a thing where, oh, let me introduce the puzzle. You can move this one left, and then you can move this one right, and then you can slide this one over and then up, and then they can move around, but they can't overlap each other. The goal is to get this red one into that slot. I swiped this puzzle from a Professor Layton game, in case you play Nintendo DS. Cool little game. Most of the puzzles are lame, but this one was pretty awesome. It took my wife several hours to solve it, and my wife is an amazing puzzle solver. So I coded up the solution and found the optimal solution. And now you will too. Yeah, so the sad thing about AI is the more you study it, the lamer puzzle games get, because you start trying to solve the puzzle and you think, I could just code this up. And then you no longer want to do it anymore. And it kind of ruined chess for me, and it sort of ruined Professor Layton for me, and these are really good for your brain. People really should spend time doing puzzles, but I just want to code them up every time, and half the time I do go code them up and get the optimal solution and blow everybody else away. Sorry, that's what AI is going to do for you too. Okay. I'm not trying to get from here to there, so how would you use uniform cost search? Well, do you see that taking a step is, if I were to generalize, taking a step is just an action, right? I could have a set of, say, 4 possible actions. There's 1 action, there's 2 possible actions, there's 3 possible actions, there's 4. So my set is north, south, east, west. What's my set of possible actions in this puzzle? I can move this one to the left, I can move this one to the right, I can move this one up, I can move this one down, so on and so forth. In the case of the path search, if you happen to be right here on the left edge of the screen, you actually don't have 4 actions, you only have 3 actions, right? There are cases where you can't do all of your actions. Likewise, in this puzzle, if you're right here, one of your actions is move the red block up and left and down and right. All 4 of those actions are not acceptable now because in all 4 cases they overlap. So you don't actually have those actions, but you can move the orange one to the left. You can't move it up or right or down, but there is a set of actions. There's actually 44 possible actions.